Hey Diana, this is the video about buffers. I looked at the homework questions that you sent me and I made a little list of like the topics that were on the homework. And so I'm going to just go through them and do a few of the homework questions with you. But hopefully, even in an hour, you can probably get like 80% of this kind of checked off, which might end up being kind of enough to do well on the test. So let's get into buffers. All right, so let's talk about like what is a buffer. So a buffer is a solution that contains high concentrations. And so what we're talking about is high molarities. High is a relative number, so don't worry so much about where the cutoff is, but just reasonable molarities, high concentrations of both a weak acid and its conjugate base, or, so this is kind of option number one, or option number two, a weak base and its conjugate acid. So let's kind of flesh this out a little bit here. So that's what a buffer is. Actually, before we flesh that part out, let's also say the point of a buffer, the purpose of a buffer is to resist drastic fluctuations. I'm not even going to know how to spell that. Fluctuations in pH. So the point of a buffer is to kind of keep your pH relatively stable. And so we'll talk about how all that works. But let's come back to what the buffer is made up of. So there's really two options. The first one is probably the more common, the weak acid and its conjugate base. But the other one is, is also somewhat common. So we want to make sure we talk about it. So these two bottles would represent buffers. Okay, so the first option is when you have a weak acid and its conjugate base. So first of all, it's obviously very important to remember what ones are the weak acids. And the way that you know the weak acids is that they're not on the list of strong acids. So really quickly, just jotting the strong acids down once more. Hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and then the only one that's a diprotic acid, sulfuric. None of these can be in buffers. These cannot constitute a buffer. They cannot kind of be present in a buffer because they're strong acids, and a buffer needs to have a weak acid and its conjugate base. So none of these are going to be options, but of any other acid can make, because any other acid would be a weak acid, that could be the basis for a buffer. So let's kind of use, I don't know, a good one would be hydrofluoric acid. So if you have hydrofluoric acid in your solution, as long as you all, and let me give a relatively decent molarity, 0.100 molar is kind of like a very common molarity. But you can't just have a weak acid. That would not be a buffer. You would also have to have its conjugate base. So just to remember, what is the conjugate base of HF? The way to figure out a conjugate base is literally just react it with water. Make it donate its proton, because that's what acids do. They donate their protons. This is the thing that we've been doing a lot of, and you know already pretty well. It makes F minus. Once it donates its proton, this is the conjugate base. So you need its very own conjugate base, not somebody else's conjugate base. You need his conjugate base. So this is the conjugate base of this acid. The key here, though, is that you're not ever going to be able to just have F minus because all compounds have to be neutral. So when the conjugate base, when you're talking about this species here, it kind of comes into the buffer as a salt, it will have what's called a counter ion. And honestly, it's almost always sodium. It could be potassium, but it's usually sodium. This is the counter ion that will kind of be there to provide a charge balance for the F minus so that you get the overall compound to be neutral. So in other words, when on the questions, you'll see something like the buffer contains 0.100 molar HF and 0.100 molar sodium fluoride. But you have to kind of understand that the sodium fluoride, the important part of that is the fluoride ion. It's not really the sodium. He's just the counter ion, and he actually doesn't really do anything other than just kind of be there to keep everybody neutral. But this would be a buffer because you have both a weak acid and you have his conjugate base, which will come in the form, I'm going to say, in the salt. And the salt just being the ionic compound that has the counter ion. That's the salt. All right, so that would be a buffer because you have both species. But the other option is to have a weak base and its conjugate acid. Now, weak bases, honestly, I'll just give you like the two most famous ones. The two most famous weak bases are probably ammonia, which is NH3. And then there's this other one called CH3NH. I'm trying to remember if it's NH. Let me look at it real quick. Just because the weak bases are, CH3NH2. These are kind of very famous weak bases. So let me just pick ammonia. So you'd have to have the ammonia. Let's just use 0.100 molar NH3. But this alone would not be a buffer. You would need to also have his conjugate acid. His conjugate acid, not somebody else's, but his. So how could you figure out what that conjugate acid would be? Just react it with water. But understand, it's a base. So bases are proton acceptors. And in this case, the water will be doing the donating because the water will act as the acid. This is all the review from the last chapter. The two products would be NH4 plus and hydroxide, OH minus. So this is the conjugate acid of this base. This one is his conjugate acid, ammonium, NH4 plus. But similarly, you're not just going to have a positively charged ion swinging around by itself. You need a counter ion. And I'll tell you that almost always the counter ion that's chosen is the chloride ion. It could be another one like iodide or bromide, but chloride is super, super common. So you'll see this presented on the paper as ammonium chloride or NH4Cl. And like usually you'd have maybe 0.10 molar, some kind of molarity of it. So here's a buffer, a weak base and his conjugate acid within the context. I'm going to write it again, in the salt. Because you're going to have that counter ion of chloride, but you're not going to care about the chloride. It actually doesn't do anything in the buffer. So that's how a buffer is made. It has these two components. Some of the questions on the homework said something like, which one of these will make a buffer? So let me just address that really quickly here. If you have, let me write which is a buffer. If you have a question that says, all right, so like say it says 0.100 molar HBr and 0.100 molar NaBr, you would have to recognize that this is not a buffer because this is a strong acid. Strong acids cannot make up buffers. They have to be weak acids and their conjugate base. This is the conjugate base of hydrogen bromide or of hydrobromic acid, but this is a strong acid which disqualifies it as a buffer. However, if someone wrote something like this, 0.100 molar H and then this, and 0.100 molar Na C2H3O2. This would be a buffer because this is a weak acid. It's called acetic acid, but even if you didn't know his name, you can take a pretty good guess that it's an acid because it begins with an H. And it's not on your list of strong acids, so therefore you can assume it's a weak acid. And this is his conjugate base. This is the acetate ion, which is present with the counter ion sodium plus. Whoops, that should be a minus right there. So you've got a weak acid and his conjugate base. You've got concentrations of both, so you're good to go. Now, so that would be a buffer. Let's talk about how a buffer works. So the purpose of a buffer is that it's going to resist pH change. Let's talk about what that's all about. So I'm just going to choose probably a very famous buffer, which is the hydrofluoric acid buffer. Let's just say we've got 0.125 molar. Doesn't have to be 0.100 of hydrofluoric acid, and you've got 0.150 molar of NaF. That would be a buffer. Notice I use two different concentrations. Just in case it shows up, I didn't see any questions about this, but an ideal buffer would have, if they call it ideal, and that's kind of a famous word, would have equal concentrations of both. So ideally, the buffer actually works best when they're equal. But as long as they're both kind of close to each other, like in the same world, then it would be a functional buffer. But I'm going to leave that alone. But an ideal buffer would have them be equal to each other. All right, so let's talk about this buffer here. So the whole point of this buffer is to be able to handle or to deal with you kind of adding small amounts, so drip, 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 small amounts of either a strong acid or a strong base. Let me deal with the strong acid first. If you add in to this buffer, let's just say, let's say hydrochloric acid. Hydrochloric acid. Hydrochloric acid is a strong acid. Let's just, and by the way, with buffers, you're always going to be dripping in strong acid or strong base. That's like the only context that it really matters. So the addition, what you're going to be adding is going to be strong. But let's deal with adding in strong acid first. If you had just added in hydrochloric acid to plain water, so pretend this was plain water for a minute, your pH would plummet. Because if this was plain water, actually let me even address that really quick off to the side. If this was just pure water, and I drip, drip, drip in some hydrochloric acid, my pH would be around, 0 to 1. Your pH is going to be so low. Because don't forget what a strong acid does. Strong acids completely donate their protons, all of them, every last one of them, goes to the water molecules that are in there. And you're going to get a ton of these. And these hydronium ions are what makes your pH very, very, very low. So hydronium ions, actually that's what pH measures, is how many hydronium ions you have. And if you get a ton of them, your pH goes way down to 0 or 1, something like that. So that's what would happen if you dropped it into pure water. Your pH would go way down. When you drop it into a buffer, something different happens. Okay, so let's talk about when you drop your strong acid into a buffer. The reaction, let me write the word relevant reaction, because that's kind of the terminology that we're going to use, would be that the hydrochloric acid, instead of actually interacting with the water molecules, would have someone else very important to interact with. So this is an acid, so he's got to react with a base, right? Well, you have a base here in the presence of the fluoride ion. Because remember, that's an acid, but that is called a conjugate base. Conjugate bases are bases, conjugate base. So the relevant reaction the hydrochloric acid would essentially seek out, because actually this fluoride ion is actually a better base than the water, because you would even call him you would call him a base, like he's a weak base, but he is a base, conjugate base. So the acid here, let me kind of review here, that's obviously the acid because it's hydrochloric acid, would react with the base, and you would, as usual, get this transfer of protons, acid to base. And the two products would be HF, because he would donate his H to the F minus, and that would get you HF. And you would have the Cl minus. Okay, so really what happens here, and this used to confuse me, you actually turn the hydrochloric acid, which was a strong acid, you actually just essentially turn it into a different acid, which is hydrofluoric acid. However, it's a really good exchange. In terms of what's going on in the solution, you take a strong acid and you essentially turn it into, through a chemical reaction, you turn it into a weak acid. And that is a very good exchange. If what you are trying to do is keep your pH stable, that's a very good exchange for keeping your pH stable. Because the strong acid would have killed your pH by producing a ton of hydronium ions, whereas the weak acid, which you kind of flipped it into, you turned it into HF instead, and the chloride ion, but the chloride ion is just one of your pH neutral ions. If you remember your pH neutral, he was on your list, so he's not going to do anything. The weak acid, it will produce a few hydronium ions, because remember, weak acids are also acids and they donate their protons. However, not very many of them, only like 1% of them do it. So you're just going to get a few of these hydroniums. And so your pH will stay more stable, whereas this would have given you tons of hydroniums. So hopefully you see it's just kind of a neat little trick or whatever that the solution will do. Let's talk about what happens if you have added in. So by the way, notice that the hydrofluoric acid that was originally present in the solution doesn't react. The hydrochloric acid is not, acids don't react with other acids. Acids react with bases, okay? This is just an underline, by the way. Acids react with bases, so that will kind of engage that part of the buffer. But let's talk about what happens if you drip in to your buffer some base. So if you add in some, let's say some KOH. KOH is a strong base. He is a group 1 metal hydroxide, and it's a strong base. Now the one thing about this is that when you are dealing with strong bases in this whole chapter actually, I highly recommend, understand that the strong base really is just, all that it does is it makes these hydroxide ions. We talked about that before, it just dissociates. This part of the strong base is not a player. You can completely ignore the front of all strong bases, pretty much for the whole chapter. So when someone adds in potassium hydroxide, pretend the potassium is not even there. Hydroxide is what's reacting, okay? So let's think about who the hydroxide is going to react with. He's a base, okay? That's going to be a base. Is he going to react with the other base, the F minus, which was the conjugate base? Or is he going to act with an acid? Well, bases will engage acids. So the relevant reaction here would be, let's go ahead and write it. The hydrofluoric acid will kind of engage and react with the incoming hydroxide, which by the way would have really killed your pH and driven it way high towards 14. But the buffer is going to handle it. So let's see what the buffer does. This is your acid, weak acid. This is obviously your base. Which way does the proton go? Acid to base. So the two products would be water and F minus. So once again, it's kind of a good exchange because what you've done is you've turned this strong base, hydroxide, you've kind of, because of the buffer reaction that happens, you've kind of turned it into, well, you've turned it into water, which is neutral, so that's wonderful. And what you've turned it into is really the conjugate base species of hydrofluoric acid. So F minus obviously is the conjugate base of this acid. But at the end of the day, this conjugate base is a weak base. It's not a strong base. It's not a group 1 or group 2 metal hydroxide. It's a weak base. And so therefore, on the pH scale, sure, it will push your pH up a little bit, but not a lot, like a strong base would. And so it resists pH change. So it's, again, it's kind of like the same trade-off. If you drop in a strong base, it will react with the acid part of the buffer, which will turn it into a weak base and water. So that's the whole point of maintaining a stable pH. So that's what buffers, that's how they work. Let's go ahead and use this buffer here to now talk about how to, and by the way, we will end up using that same concept in some of the next questions. Let's talk about calculating the pH of a buffer. You will be asked several times to calculate the pH of a buffer. And that's different than calculating the pH of an acid, like a weak acid. Remember, you need to use the ICE tables. Or calculating the pH of a weak base, you need to use the ICE tables. A buffer will have both a weak acid and its conjugate base. So it really has both species present, and they will most likely use the terminology calculate the pH of a buffer containing, let's just say containing this and that. And let's talk about calculating it before you've added anything to it. So let's just go ahead and just say, someone made a buffer, these are the two concentrations, what's the pH? There is an equation called it's called the Henderson-Hasselbalch equation. I'm just going to call it HH. And it's you need to know it, probably the most important equation in this chapter. I usually write the pH of a buffer. That's how I write, because it's important that you only use this for buffers. The pH of a buffer is equal to the pKa plus, and make sure you use a plus sign here, plus the log of the concentration of the base over the concentration of the acid. Okay, so that's the Henderson-Hasselbalch equation. Let's go ahead and use it to calculate the pH of this buffer. Okay, so to calculate the pH of this buffer, we need the pKa. Now, a couple things about pKa. The pKa, as we talked about this before, is just the negative log, because that's what P means, negative log of the Ka. So as long as you know the Ka, you can get the pKa. And actually, I need to give you the Ka of HF. This would have to be provided on the test. 6.8 times 10 to the minus 4th. And I just got that from the list of Kas on page 739. Okay, so let's go ahead and get the pKa of HF. So negative log of that number. I got 3.17. Okay, so that's the pKa. Now, on occasion, they may give you a Kb instead of a Ka. All right, so just here's how you would have to handle that. You can't use pKb. You've got to use pKa. This is a non-negotiable. But if all that they gave you was the Kb, because they might in the question, and they would call it a Kb, just get the negative, take the negative log of it and get what's called pKb. And then these two actually have an interesting relationship. Kind of just like pH and pOH have to add up to 14, these two always have to add up to 14. So if you are given a Kb, just get the pKb and then subtract it from 14 and that will get you the pKa. It's kind of a backhanded way of getting pKa a different way, but you've got to get the pKa. So what did I say was 3.17? Plus the log of the base over the acid concentration. So these are the molarity concentrations. So it's important to know which one is the acid and which one's the base. Honestly, it's pretty easy. Even if you're getting one that's unfamiliar, the acid is the one with the extra hydrogen. I mean, this one I know you knew that was an acid, but like if you're looking at it and you're like, I don't know which one's the acid or the base. The acid is the one that has the extra H on it, and then the base would be the one without the H. So obviously that's the acid. So, but we need the base on top. So we need the concentration of the base. And so it's 0.150. And then over the concentration of the acid, 0.125. What I would do with this Henderson-Hasselbalch equation is just get this piece first. So 0.15 divided by 0.125. And then, and I got that's 1.2. And then take the log of that number. And then you're going to add that to 3.17. And I'm getting that the pH of this buffer is 3.25. Let me just make sure that that's correct. So 0.15 divided by 0.125. And then we want the log of that number. And then we're going to add that to 3.17. Yeah, 3.25. Okay, so anyways, that would be the answer. That's the pH of this buffer. Just looking at your homework questions that you sent me, let me just pull that up real quick. Like for instance, there's one that you sent me that says part A, it says a solution that is 0.195 molar in acetic acid and 0.125 molar in potassium acetate. That would just be Henderson-Hasselbalch equation. Same with part B, the solutions that's 0.195 molar in the CH3NH2 and the 0.130 molar in the other one. That is same thing, just Henderson-Hasselbalch equation. For these ones, you will have to look up the Ka for part A. So this is just the one that you sent me here. For part A, you're going to have to look up the Ka for acetic acid. It is on page 739. And then for part B, you're going to have to look up the Kb for CH3NH2, and that's on page 755. And so, and keep in mind, the CH3NH2 is the base. So that's the one that goes on top. The other thing with the ends in Br, that's the acid. That goes on the bottom. Because notice that's the one with the extra H. Remember, the one with the extra H is the acid. So that one here, though, you're going to have to look up the Kb, and you're going to have to go this route. You're going to have to get the pKb from that, and then you're going to have to find the pKa, because Henderson-Hasselbalch demands pKa. Okay, so those two are that type of question. Now, let's go ahead and do another kind of easy type of question before we move on to a little bit harder stuff. So, choosing a buffer. Choosing a buffer system. For this one here, it's just like a rule. A buffer works best when the pH is close to, and when we say close to, we mean like within 1, either higher or lower by 1, the pKa. So this is really kind of simple here. There was another one that you sent me about which buffer to choose. Sorry. Let me see if I can find it. This is it. It says part A, which of the following buffer systems would be the best choice to create a buffer with pH equal to 9.05? So if your pH is equal to 9.05, your best buffer would have a pKa near that. So what you would be doing is you would have to look up these Kas, okay? So and they would have to be given to you on a test. It's not like you know the Ka. So these are the choices, HF, KF, so hopefully you can find that here. So HF has I think that was the one that we just did. His Ka is equal to 6.8 times 10 to the minus 4th. And the Kas would all be on page 739. HNO2, his Ka is equal to, it's written on that page, 4.6 times 10 to the minus 4th. And then NH3, okay, NH3, you're going to only get a Kb because that's actually a weak base. The Kb would be, I think it's 1.8 times 10 to the minus 5th. I actually have that one memorized. Don't really know why. I'm going to make sure though. Yeah. So if you're given a Kb, you're going to have to get the Ka from that. Oh. And okay, the two equations that you can use, these two, pKa and pKb, have to add up to 14. However, if you're just trying to deal with the Ks, like no Ps, right, just the Ks, the relevant equation is that Ka times Kb, be careful, it's not plus, Ka times Kb always equals 1.0 times 10 to the negative 14. So let's go ahead and get the Ka for, it's actually going to be the Ka for his conjugate acid. That's really what that is. It's the Ka for the conjugate acid, because Kas are always about acids. But still, you need the Kas for this evaluation, because it's all about, you know, it ends up all being about the pKa. So let's go ahead and get, let me do that real quick. What's the Ka? 1.0 times 10 to the negative 14th. I'm going to let my calculator read that, and then I'm going to divide by the Ka, sorry, the Kb, 1.8 times 10 to the minus 5th, to get the Ka. And it's 5.56 times 10 to the minus 10th. Let me just stop with those three here. So if I then take find the pKa of all of these by just taking the negative log. So let me take the negative log of this number here, 6.8 times 10 to the minus 4th. The pKa of this one, oh, we just did that one. That was 3.17. But what's the pKa of this one? Let's do the negative log of this. 5.56 times 10 to the negative 10th. I'm getting 9.25. So this is the answer. This would be the best buffer, because see how the pKa is right near, within one of this one? See how close they are? So you're looking to choose the one that has a pKa near the target pH. But why this was a little bit complicated was because the correct answer was one that was really, you had to get the Kb, because the Ka value for this is not published. You'll notice it's not in the tables. So you have to find it. You have to find the Ka kind of backhanded way through this. Anyhow, that's how you're going to choose the buffer. Find the one that has the closest pKa to the target pH. All right, so moving along, let's go ahead and do probably the hardest part of this, which is calculating the pH of a buffer after the addition of like strong acid or strong base. So with this one here, this was actually the first image that you sent me. And it was like, what is the initial pH of the solution? What is the pH after adding 150 milligrams of HBr? So the only issue here is that I didn't see the left side of the question, which kind of gave me the original solution. So actually, I'm just gonna like, let me see if this one came from our textbook, because if it'd be sweet if I could find it. Hold on a second. The exact same one that was here, but okay, so let's see here. Oh, I bet you it's this one. Yeah, it is. It's probably question number 48 on page 838 because it looks like it matches. And the kind of beginning information says 100 ml solution of buffer solution. Buffer solution is, and then they give us the starting concentrations. It says 0.175 molar in HClO and 0.15 molar, 150 molar in NaClO. So you can see it's definitely a buffer. It's got a weak acid, because that's not on our strong acid list, and his conjugate base. See how it's embedded in the salt with the counter ion sodium? Okay, so that's that. And then it says, what is the initial pH? So part A is just what is the pH of the buffer? That is the Henderson-Hasselbalch equation. So if you want to pause the video, see if you can do it, but I'll just kind of proceed with it. The pH of a buffer is going to equal the pKa plus the log of the base over the acid concentrations. So all I need to do is get the pKa of the acid. And if I look up HClO on page 739, the Ka is 2.9 times 10 to the negative 8. So his Ka is 2.9 times 10 to the minus 8. 2.9 times 10 to the minus 8. That is the Ka of HClO. So pKa, which is what I need. I need the pKa, is the negative log of the Ka, the negative log of the Ka. So if I take that negative log of this number, I am getting 7.54. And then I'm going to add the log of the concentration of the base over the acid. So I got to make sure I put them in the right order. The acid is clearly this one. That is, see how it has the extra H in it? That's the acid. So that's 0.175. And the base is this one. That's his conjugate base. That's the conjugate base of this. So that's the base. And that's 0.150 molar. And so I just put that all in my calculator. Plus the log of 0.15 divided by 0.175. And that is 7.47. So that's the first answer. That's the pH of the buffer before you've added anything into it. So like really what we're here is we're at this stage where you have HClO and the NaClO. It's just sitting there. You haven't added anything to it. Now part B is the new part. Part B is called calculating the pH. I'm going to erase it. Calculating the pH after you've added something to it. So part B, just going to grab, oh wait, it's on my phone. Said, calculate the pH after you add, after the addition of 150 milligrams of HBr. So notice now we are adding in, remember how we talked about adding in a strong acid? HBr is actually on your strong acid list. So it's kind of just exactly what we were talking about before. What you have to learn is a new type of table. So this is basically called after adding either strong acid or strong base to a buffer. You need what's called a before addition after table. It's not the same as an ice table. It kind of looks a little similar, but it's not the same. And I'll show you how. Okay, so a before addition after table. This is what you're going to use for any question that's talking about calculating the pH. Let me write, it's usually about the pH. Calculating the pH after you've added something to a buffer. Not just the buffer chilling, but after you've added something into it. Okay, so before addition after table kind of looks like you're going to write before addition after. And you're going to write the relevant reaction along the top. So really, what reaction is happening? Well, obviously the hydrobromic acid is going to react with something. What part of the buffer is he going to like mess with? Is he going to react with? Is an acid going to react with another acid? No. An acid is going to react with the base. And it's really important that you don't include the counter ions. There are spectator ions, they don't do anything, and it's going to kind of mess with you. So keep in mind, remember that ClO, it's really the ClO minus ion balanced out with the Na plus. So see how I wrote the ion back in there? It's just like sodium chloride, it's just a different ion. It's a polyatomic ion. It's called hypochlorite, but ClO minus. That's the part that's going to react with the hydrobromic acid. This is the acid, that's the base. Proton donor, proton acceptor. So same thing as usual. We can kind of reuse old things here. And you're going to use a full forward arrow for these because this guy is strong. It pushes the whole thing to the right. So the strength, and it's always going to be, with these tables, by the way, it's always a full forward arrow. Okay, let's see what happens. So he donates, that H is going to be given to ClO minus. So that's going to become HClO. Because he's giving this hydrogen, he's giving that to the ClO minus. So that becomes that. And what's left over would be Br minus. Okay, the biggest difference with these tables in comparison to ice tables are ice tables use molarities, capital M concentrations, molarities. Whereas before addition after tables, this is huge, they use moles. Moles, not molarities, moles. So you can't put molarities into this. You've got to put in moles. So this is essentially how you're going to fill this out. Before we've added everything, so this is before you've added anything, this whole row. What did we have in our beaker? Well, if I'm remembering correctly, it was 100 mils, and so 100 mils is 1.100 liters. Right? It was 100 mils of 0.175 molar HClO. Okay, so the way that I would do this is this. To get moles, I think probably the fastest way to just do this is like this. To get moles, you're just going to take the liters and you're going to times it by the concentration molarities. So the amount of liters times by the molarities, that's going to get you the moles. So to get the moles of HClO, because because before we've added anything, you have this and you have this. These are the two species you have before you've added anything. To get the moles of HClO, we're going to use the liters, which was 0.100 liters, because that's the same as 100 mils. And we're going to times it by the molarity of HClO. That is 0.175, 0.175 molar. And so the moles of HClO right here is 0.0175. And the way I did that in my head, but you can just times 0.175 times 0.1, and you will get 0.0175. So that's the moles of HClO before I've added anything. And to get the moles of the other one, the ClO minus, it was also 0.100 liters, but his molarity, if you look in the question, was 0.150, 0.150 molar. And so this one is 0.0150. So just 0.150 times 0.1. Yeah. Okay. And before you've added anything, you didn't have any of these things. So all you fill in is what you had. You just had a buffer, and these are the moles of each that you had. We got moles by timesing the liters times the concentrations. Okay, now in the addition row, all you write is what you add. It's not like an ice table where every piece gets filled up. In fact, I don't even write anything in the empty spots. You just write what's relevant. It's kind of like a checkbook. You only write what you're trying to keep track of. So what are you adding? You're adding HBr in part B of the question. B of the question, it is saying after the addition of 150 milligrams, so 150.0 milligrams of HBr. So how many moles of HBr are we adding? Well, this is just turn it into moles. So I'm going to do this in my head. That's 0.150 grams. I just turned milligrams into grams. You just divide by 1,000 to get it into grams. So this would just be a gram to mole conversion because this time they're giving us grams. So HBr, Br is 79.9 and H is 1.01. So 80.91. So 80.91 grams per mole. 0.00185 moles of HBr is how much you're adding. 0.00185 moles of HBr is what you're adding. Okay, so here you have to look at, okay, if you've added this much, these are the two reactants. You have to think about which one is the limiting reactant, which one is the smallest amount, and it's clearly this one here. And remember, a limiting reactant will fully react and it will drop down to 0. A limiting reactant completely gets consumed. So after the whole reaction is done, the limiting reactant goes down to 0. The one of these two, the smaller one, will drop down to 0. This one, you will react as much as the limiting reactant allows you to react, and you'll notice it's a 1-to-1 ratio. So this much is how much of this reacts. So you just want to subtract the amount of the limiting reactant from this one. So 0.0150 minus 0.00185. That equals 0.01315. And then these ones here, you're going to add the limiting reactant. And by the way, this ion here is irrelevant because you'll notice, as we talked about a couple days ago, he is one of your pH neutral ions. And it almost always will be because it's going to be, they're always the ones that were kind of part of a strong acid. If you remember, that's how we define the pH neutral ions. So irrelevant. We're not even going to think about what happens to the strong acid is kind of irrelevant. It's this part that matters. So we're going to add the limiting reactant amount to this one because this is getting created. We're producing extra of this during this reaction. So I'm going to add 0.0175 plus 0.00185. And I'm getting 0.01935 moles of that. Okay, so now when you look at it, and the whole point was to calculate the pH. When you look at it, what do we have? Well, we still have a buffer. We still have ClO minus and HClO minus. And that's really good because that means we can come right back to the Henderson-Hasselbalch equation. pH equals pKa plus the log of the base over the acid. So the pKa, I'm forgetting what it was. I got to do it again. It's the negative log of the Ka, which was 2.9 times 10 to the negative 8. The pKa was 7.54 plus the log of the base of the acid. Now, normally in Henderson-Hasselbalch, you're supposed to use concentrations. With a before addition after table, you actually can just use the moles. You're allowed to just use the moles. You don't have to divide by the liters to get moles per liter or molarity because the liters are the same. And so the two denominators are the same. That might be a little bit confusing. But key here is that you are allowed to use either moles or molarities. You're actually allowed to use either. And since we have moles, remember that these tables always use moles, we can just go with that. We're just going to use the moles and you'll get the right answer. So base on top. Which one of these is the base? It's this one. 0.01315 divided by the acid 0.01935, and then we just do math. So plus the log And so I'm getting a pH of 7.37. Okay, and so I want you to see a couple things here, because this comes up in a different question too. That's the pH after you've added a little bit of hydrobromic acid into it. So after you drip in some acid, the pH did go down. Notice before it was 7.54. No, it wasn't. It was something else, but I can't remember what it was. But it was above this. It was something else, but it was higher than this. When you add in an acid, whoops, if this is the pH scale, 7, 14, and 0. If you add in an acid, of course it's going to push your pH down, but not all the way down to 0. See how it pushed it just a little bit down? I can't remember what the answer was before, but it was just a little bit above this. So yes, it decreased it, but that's what an acid would do. But the key here is it doesn't have drastic fluctuations in pH. It just decreased it a little bit. I don't think I'm going to have time to do part C with you, but the only difference with part C is that it's just a different relevant reaction. The relevant reaction, maybe I'll just get that part done with you, with part C. The relevant reaction is you're adding sodium hydroxide this time. So you're adding in sodium hydroxide. So keep in mind, remember I said that with strong bases, don't even think about the sodium. Just think about it as if you're adding in hydroxide. So the relevant reaction would be, what part is going to react with the hydroxide? Well, of course, it would be the acid. Acids are what react with bases. So this part will engage the hydroxide. Acid, proton donor, proton acceptor, that will get you H2O and ClO minus. And you can just reuse the numbers. I've erased them, but reuse the numbers for the before. You know, we had this number, and we had this number. Just keep it all organized. I can't remember what it was. You're going to figure out the moles of OH minus that you're added. Which one is the limiting reactant? It's probably going to be this one, but it's just choose whatever one is smaller. I'd have to calculate it. Choose whatever one is smaller. The limiting reactant drops down to 0. You subtract the limiting reactant from the other reactant, but you add it to the products, and then just get your new pH. I can guarantee you that if you are adding in a base, it is going to push your pH up towards 14. A base would do that, but you'll see how much it actually does, but you have to calculate it. I want to mention, I think on the next part A of the next slide, it says, which of the following substances will raise the pH of this solution upon addition? And it says a formic acid solution has a pH of 3.25. Okay, so what that is, formic acid, I think is HCHO2. But they're basically saying you just have the acid. And so it's not a buffer. And its pH is 3.25. So which one of those will raise the pH? Okay, if you add in KCl, that's the first choice. KCl is a salt. It's not a classic acid. It's not a classic base. It doesn't start with H and it doesn't end with OH. And it's not ammonia or whatever. So you have to think about what are the two ions, K plus and Cl minus. These are both on your list of pH neutral ions. So this will not affect your pH at all. HCl is a strong acid. If you drip in HCl in here, that's going to lower your pH down towards 0 or 1. It's not going to raise your pH, so that's not the answer either. NaBr is another salt that has sodium positive and Br minus. Those are also on your pH neutral ion list. This will not affect your pH at all. But I think the last one's probably the answer. If you add in NaCHO2, this here is a salt. It's the Na plus and CHO2 minus. This here is the conjugate base of that acid. And if you put that in there, it's going to raise your pH because it's a base. The conjugate bases of the weak acids are going to be bases, and they're just weak bases. They're not like the strong base club. They're not like this, but they're still bases, and they will raise your pH. So that's the answer, because that's the only one that one is, by the way, another way to say it is, remember how we did the ions? This is the basic ions. Remember how we had that list on the board and it said all other anions except for the ones that we listed, which contained these two. So that's another way we could say it. It's a basic ion. It will raise your pH. Okay, so I wanted to mention that. I think we're going to have to move on to the last thing about, which is KSP. So luckily, KSP is, at least to a level, you can get a lot correct, at least on the ones that I looked at that you sent me, in a short amount of time. So let's make sure you know how to do KSP. And I think I'm just going to actually use the ones that you sent me to show you how to do it. So let's see which one. Okay, it starts with the thing that says enter a balanced equation for the dissolution of CaCO3. That's really when the topic begins. Okay, so let me introduce this whole thing. KSP is called the solubility product. That's what the SP stands for. Constant, but it's really an equilibrium constant. So I'm going to write that in there. The solubility product constant. Solubility product equilibrium constant. So it's just a K, just like any other K. The key here is that whenever you have KSP, almost immediately, what you want to do, because I think you pretty much always have to do it, is you always write what's called the dissolution. Although I would call it dissolving, but to be honest, it's also dissociating. It's whatever makes you feel like you're getting it. It's all three things happen, but dissolution and dissolving are synonymous. But when ionic compounds dissolve, they dissociate, which is break apart. So whatever way you want to think about it, as long as you get there, just use that. But that's what you want to do. You want to write, whenever you're even having a question that involves KSP, you want to write the dissolution or dissociating reaction. So that's why it started with that question when it started introducing the topic. So let's just do that together. So what I'm looking at is the one that says enter a balanced equation for the dissolution of CaCO3. So the thing about these reactions is that they always have only one reactant. We're so not used to writing those. We're so used to writing two reactants because we've just been doing acids and bases, and there's always like acid to, reacts with the base. But when you're doing KSP or writing a dissolution reaction, that's what you write. You write the compound as a solid. That's important. And what we're describing in this reaction is just how it dissolves, pretending that you're dissolving it in water. Now, we don't write water because it's not reacting with water. It's not creating new compounds. It's just dissolving into the water. So you just write the compound as a solid, double arrow, because with these things we're seldom completely dissociating it, double arrow. And then you just have to write which ions you get. So keep in mind everything that you learned from your periodic table, this comes back here in this chapter. The whole thing about there's a pattern to the ions. Remember, noble gases don't do anything. So 1- is the fluorine part. 2- is where oxygen lives. 3- is where nitrogen lives. And then group 1, group 2. And group 3 is where aluminum lives. So the ion that calcium makes, calcium's in the second column. So that's how I know that it's Ca2+, because it always makes the 2+ ion. And so when this compound dissolves, remember that the two ions separate, and that's why we're listing them as separate. And then the other ion, you have to just kind of recognize the ionic compound, it only has one cation and one anion. So if that's the cation, that whole thing is the anion. Even if you don't recognize it, that thing is carbonate. And can you figure out what the charge would be? Because there's only one carbonate to balance out one calcium. So hopefully you see it's a 2- charge. That is the dissolution reaction. It shows it dissolving. And when it dissolves, it dissociates. That's why I'm saying you can kind of call it either. It breaks apart. So that would be the answer to that one. Let me show you just another one just to make sure you're getting it here. If someone asked you to write the dissolution reaction for MgBr2, you would write it as a solid. You're showing it dissolving. Now, with this one here, what is the charge on the magnesium? The charge on the magnesium, it's in the same column as calcium, it's 2+. But bromine is in this column, the 1- column. The key here is there are 2 bromines. So the way that you have to write it is like this. There are 2 bromide ions. Because that's what that compound is. I mean, if you had to picture it, if you could see it with a microscope or whatever, it's 1 of them and 2 of them, and that's how you get neutral. So you just represent it like that. When it dissolves, you'll get 1 of him and 2 of them. That's a dissolution reaction. Okay, now let's stay with this for a little bit here. With this one here, let me clean this up a little bit. You can write a KSP expression for this. The KSP is just the K, just the equilibrium constant for this chemical reaction. It's the K for the dissolving reaction. So all Ks are products raised to their coefficients divided by the reactants. So let's do the products first. So it would be the product side would be Mg2+, products go on top, times the other product, which is Br-, raised to their coefficients, right? Because the 2 becomes the coefficient. Remember, in equilibrium chapter, the coefficients become the exponents. Now, divided by the reactants. However, what you're going to notice is for KSPs, the reactant was always the solid, because the whole point of a KSP is showing the solid dissolving. So nothing shows up down there because solids are never included in equilibrium constants. So that is your KSP expression for MgBr2. This would be your answer. You had several questions that you sent me that were similar to that. Let me see here. Let me see where it was. Writing KSP expressions, like for instance, like part B says, identify the correct KSP for the dissolution of CaCO3, and see if you can figure that one out yourself. If you want to think about it, pause the video. But I've already erased the thing, and I'll just tell you the answer right now. So it's the second one, because that's the second choice is the right answer, because that's what you would get for the dissolution reaction. For part C, enter a balanced equation for the dissolution of PbCl2. It's almost going to look exactly like this: Pb2+ plus 2 Cl minuses, and the correct KSP expression would be super similar to what we have here, but just lead and chlorine where magnesium and bromine are. So it would be the 5th choice. Do you see that? It would be, wait, 1, 2, 3, 4. Nope, sorry, 6th. It's the 6th choice, because Cl- would be raised to the 2nd power. Part E, enter a balanced equation for the dissolution of AgI. I'll just do it real quick. AgI, solid, dissolves and becomes this separate from this. Now, silver, you're going to find is a, you might not know the charge of it, but you will know the charge of one of them. Iodine is very safely known as the I- because he's right below fluorine. They always make the 1- cation. And from that, you can just infer or figure out that if he's 1-, he's 1+. So it's clearly this. So that would be the dissolution reaction, and the KSP would literally just be this times this. No powers, because they both have 1 exponent. And so that one would be the 1, 2, 3, 4, 5th choice. And then, so writing KSP expressions is not really very difficult at all. And then the last thing we want to talk about is how to use the molar solubility to calculate KSP. All right, so this is really the last thing I wanted to hit in these videos. So the molar solubility. It's kind of a difficult thing to explain, except for, let me kind of say it like this. The molar solubility, if you can just think of it as the X in your ice table that you construct with these, then you will get these questions correct. The molar solubility is equivalent in value to the X in the ice tables. So let's go ahead and do one of these together. I know that might not make sense until we actually do one together, but let's go ahead and do one together. I'm going to do part A, which says use the molar solubility, and it says 1.08 times 10 to the negative 5th molar in pure water to calculate KSP for BaCrO4. Okay, so there's something about KSP. Let me say it like this. There's something about KSP. There's something about molar solubility. And the way that you're going to unite these two concepts is via the ice table. Okay, so even if you don't quite know what to do, just start setting up an ice table because they come together when you start making an ice table. So let me explain. So ICE. What is the relevant reaction that you write on top? Well, it's if it involves KSP, it's the dissolution. It's the dissolving of it. So one reactant, O is KSP. It will start to kind of even look familiar here. BaCrO4, even if you don't know what that is, just make it a solid and dissolve it. And you really have to figure out essentially what are the ions that you get and how many of each do you get. So if you're looking at this, you're like, oh my goodness, I don't even know what this is. One of them will be obvious. One of them will fit nicely into your pattern. And if you look closely, barium is a 2+. Barium is in the second column. He's right underneath strontium and calcium. So that's your easy one, barium 2+. And then once you identify what the cation is, the rest of it is easy. Obviously, it's CrO4, whatever that is. I don't even know what his name is. I can't remember. But you can tell the charge must be 2- because you only have one of each in the ionic compound. So that is your relevant reaction. All right, and then let me show you how this works. It's easier than it seems. Solids. Just like water in your ice tables for calculating pH is always crossed out because it's a liquid. It doesn't even show up in your K expressions. Neither do solids. So in these KSP ice tables, that reactant is gone. Just cross it out. You don't even have to write anything in there. In addition, these are always going to just be zeros because before something dissolves, you don't have anything. And that's what initially means. So it's almost just implied to be a 0. And then in your change column, remember here you have to consider your coefficients. This is where you're going to use x's. Oh, actually, no. Not with this question. Back up for a minute here. When we did ice tables for acids and bases, I remember I said something, use an x when you are given the value of K. And only, I should write the word only when you're given the value of K, not when the K is the unknown. In this question that we're working on about barium CrO4, the K is the unknown. So no X's, we're not allowed to use X's. But luckily, in the question, remember I had said the molar solubility is the X. I wrote that somewhere. Yeah, the molar solubility is the X in your ice table. So when they told us the value of the molar solubility, and they said it was 1.08 times 10 to the minus 5th, that is the X. So let me just show you something real quick here. These have to go up, right? Zeros always have to go up. They can't go down. I'm going to write the X for a moment, but I'm about to erase it. Since these are both 1s, they would both just be X's because it's one of these and one of these. If this had been a 2, you would have had to write in 2x. But they're both 1s. But like I said, we know the value of x, so this is not so much an unknown. This is 1.08 times 10 to the minus 5th, and so is this one. It's the value of x in your ICE table. And now you just work this out. So obviously it just is the same number. And now we need the value of KSP. So go ahead and write a KSP expression for this. It's just going to be this. This one's really easy because there's no coefficients. So it seems almost maybe confusingly too easy, but we'll do another one. So it's just going to be the KSP expression just like we did before. And then remember, the values that go into K are always the bottom row. So these numbers are what you're putting into here. So BA2 plus just is 1.08 times 10 to the minus 5th. And you're timesing it by the other one. So you're essentially squaring the number. So I am getting 1.08 times 10 to the minus 5th squared, and I'm getting 1.17 times 10 to the minus 10, and that would be the answer for the value of KSP. Let's go ahead and just do one more, because that one was a little bit easy because they were both 1s. Let's do, and then we're going to be done because that's about a good amount to cover. Let's do the last one, or one of the other ones. Let me see here. Yeah, let's do this Ag2SO3 thing. This will work. This part B. Use the molar solubility to calculate KSP for Ag2SO3. So you're just going to write the dissolution reaction because it has to do with KSP and molar solubility. And you have to kind of understand here that there are 2 of the silvers. I think last time you saw in one of the previous ones that silver made a 1+ ion. Silver always makes a 1+ ion. And I think you either would have to know that or you would have to know that SO3 is a 2- ion. This thing is called sulfite. That is the polyatomic ion, kind of the anion part of this ionic compound. So some familiarity with kind of getting comfortable with these. Hopefully she'll give you ones that are somewhat famous, polyatomic ions, but like he's kind of famous. But anyhow, these are the ions that you would get. You would get 2 of the silvers, right? Because that's not a polyatomic ion. That's just a metal, but there's 2 of them. And then that thing is a polyatomic ion. Almost all your polyatomic ions will involve oxygen in one form or another. And there's only 1 of them. So see why I got the 2 of them, 2 of the silvers, and 1 of the sulfites. All right, ICE table, because we are kind of marrying KSP with molar solubility. So ICE table is where that happens. This gets crossed out. This is a 0. Okay, well, maybe I'll write the x's in for a minute here and then erase them because we actually have the numbers. You would actually get, this would be plus x because there's only 1 of them, but this would be plus 2x because remember with the change column you have to consider the coefficients. So if there's a 2, you would add 2x, right? However, we're not going to leave those x's in there because we know the value of x. It's the molar solubility, and that was what's given to us here in the question. It's 1.55 times 10 to the negative 5th. That's the value of x. The molar solubility is the value of x in your ICE table. Now this one here, we have to put in 2 times that number because it's 2x. So I'm going to have to take that number, 1.55 times 10 to the negative 5th, and I'm going to have to times it by 2. And I am getting 3.1 times 10 to the minus 5th. And so these are the numbers that would go in this bottom row of your ICE table. Now, we're about to, the whole point here is calculate KSP. Before you calculate KSP, just express KSP, like set up the expression so that part's kind of all set. So the KSP expression is Ag plus, but squared. Remember, the KSP expression, the coefficients become the exponents. And then times SO3 2 minus. And then what goes in here are these two numbers. So that's 3.1 times 10 to the minus fifth. But see how you're squaring that one? Because this one gets squared, times 1.55 times 10 to the minus fifth. It feels like you're doing something wrong because the 2 kind of gets counted twice. You deal with it when you figure out the amount of change, because you're going to get, it's 2x rather than x. So you feel like you've already dealt with it, but it gets dealt with again in the KSP expression as it becomes the exponent. So it feels like you're doing something wrong, but you're definitely doing it right. You have to really consider it in both parts of the problem-solving technique. So let me go ahead and finish this out. 3.1 times 10 to the minus fifth squared times 1.55 times 10 to the minus fifth. And I'm getting 1.49 times 10 to the negative 14th as my answer for the KSP. And hopefully that's right. There's always a chance I type something wrong, but I'm pretty sure that's right. So anyhow, that's how you do the KSP and molar solubility. You like bring them together in the ICE table, and a lot of them end up looking the same. The key is that you write the dissolution reactions kind of correctly. So hopefully that was helpful. I think that's probably a good place to end. There was one more thing I wanted to mention on the homework that you sent, and it was on this one that had bins, like will they make a buffer solution or will they not? Right off the top, I can tell you that the bottom 2 will make buffers, because you have both a weak acid and its conjugate base, or a weak base and its conjugate acid. So the bottom 2 are both going to make buffers. The middle one on the top row that has both HF and HCl, definitely not going to make a buffer, because you have a weak acid and a strong acid. That's not a buffer. Buffer would have a weak acid and its conjugate base. Strong acid, no. So that's not going to do, that would not be a buffer solution. The other 2, so I'm talking about it's the one on the top on the left and the right. You'd actually have to calculate, you'd actually have to kind of, because here you're actually, with the first one, you have hydrofluoric acid and you're adding hydroxide to it. You would actually have to do like a before addition after table for that and figure out what you have left after they react. And so those 2, and same idea with the other one as well, would take some time, but I feel like we're running out of time, and I also feel like, so maybe just guess on those 2, unless you want to tackle. You really need to calculate those other 2. But the way that you would do it is you would set up one of those before addition after tables and just like figure out the moles of everybody, because remember they always use moles. And then, just make one of them the before and one of them the add. It doesn't really matter which one you do is which, but you'll have to figure out which one's the limiting reactant and figure out like what you have left after the reaction is over. If you have a weak acid and its conjugate base, it's a buffer. If you only have like hydroxide left over, it's not a buffer. Unfortunately for those 2, you actually would need to calculate it. You can't just look at it. So, all right, good luck with everything and just be in touch. All right, bye-bye.